Welcome to this video on demystifying the minimum energy crossing points, MECP. We'll explore the geometry, physics, and application of singlet triplet crossings in organic emitters. While a cartoon shows a single-point crossing, the reality is a multi-dimensional minimum energy seam of crossing, or MESX, in non-linear molecules. The minimum energy crossing point, MECP, is the lowest energy kinetic gateway on that continuous seam. Singlets and triplets are orthogonal spin sectors in a spin-free, non-relativistic Hamiltonian, so different spin manifolds do not repel. This results in clean crossings, unlike same spin states that repel and form avoided crossings. Conical intersections and MECPs differ in their spin state and core driver. Conical intersections involve same spin states driven by non-adiabatic coupling, leading to internal conversion. MECPs are different spin states driven by spin-orbit coupling, leading to intersystem crossing. The total Hamiltonian is a sum of the spin-free baseline and the spin-orbit catalyst. The spin-free baseline allows surfaces to cross. The spin-orbit coupling couples spin and orbital angular momentum to force the spin flip when the energy gap shrinks near the crossing seam. The rate equation for intersystem crossing is governed by the spin-orbit matrix element, the delta function enforcing energy conservation, and the thermal population of the initial vibronic level. The closer the molecule gets to the MECP geometry, the easier it is to meet the strict resonance condition. In light element organic molecules where direct spin-orbit coupling is weak, vibrational motion or distortion non-adiabatically mixes electronic states, creating a spin vibronic bridge that enables the spin flip, which is essential in TADF materials. Molecules can have identical equilibrium energy gaps, but vastly different reverse intersystem crossing rates. This is because the dynamic pathway to the crossing seam, or seam dynamics, matters more than the static energy gap between the minima. In TADF emitters, the MECP acts as an engine to reclaim dark triplets. Electrical excitation generates 25% bright singlets and 75% dark triplets. The MECP risk engine upconverts these trapped triplets back into emissive singlets. The singlet triplet crossing has a dual nature. In a normal fluorophore, the seam acts as a leak, draining singlets into triplets. In a TADF emitter, the seam acts as an engine, providing an accessible reverse intersystem crossing pathway to rescue dark triplets, leading to high-efficiency emission. Good design requires engineering the manifold, not just maximizing coupling. This means positioning the state manifold so the desired constructive reverse intersystem crossing seams are kinetically accessible, while destructive seams, which lead to non-radiative decay, remain completely hidden. Calculating the crossing involves a 6-step process. First, compute low-lying states. Second, optimize equilibrium geometries. Third, search for the MECP. Fourth, evaluate spin-orbit coupling at the seam. Fifth, analyze spin vibronic modes. Finally, estimate quantum rates. Computational methods range from practical screening using TDDFT for large OLEDs, to high-accuracy mechanistic studies with multi-reference methods, and to excited state dynamics using Shark frameworks for complex non-adiabatic and spin-orbit couplings. Molecular structure dictates state ordering, which influences seam accessibility. This leads to effective coupling, ultimately dictating emissive efficiency. By engineering the molecular geometry, we control where quantum manifolds touch, giving us macroscopic control over light itself. In summary, the physics of MECP involves clean crossings due to spin orthogonal states with spin-orbit coupling as the catalyst. Geometrically, the dynamic pathway to the seam matters more than static energy gaps. For OLEDs, locating and engineering the MECP is key to creating highly efficient TADF devices.